Welcome, everyone. Today we are diving into the frontier of additive manufacturing, designing for extreme environments. As we push the boundaries of aerospace, propulsion, and energy, monolithic alloys are increasingly hitting their physical limits. Our focus today isn't just on the materials themselves, but on how we strategically match matrix reinforcement systems to mission-specific demands at the nanoscale. To begin, we have to recognize the fundamental dichotomy in Metal Matrix Composites design. On the left, we have the lightweight mission. Here, aluminium, magnesium, and titanium dominate, where every gram reduced in an aerostructure translates to significant performance gains. On the right is the high-heat mission. In the high-pressure stages of a turbine, we aren't just fighting mass, we are fighting thermal degradation. In these environments, nickel and cobalt superalloys are the baseline for maintaining gamma prime phase stability and oxidation resistance above 1000 degrees Celsius. To master these systems, we must deconstruct them into three distinct pillars. First, the metal matrix, our continuous phase that provides the load-bearing continuum. Second, the ceramic reinforcement, the dispersed phase that dictates stiffness and hardness. But arguably the most critical and the most difficult to tune in additive manufacturing is the interface. Failure in an MMC rarely begins in the matrix or the particle. It propagates at this chemical bond. When we look at our lightweight candidates, each has a specific trade-off. Aluminium is our thermal workhorse. Magnesium is the ultimate lightweight option but requires extreme interfacial control due to its susceptibility to galvanic corrosion. Then we have titanium, the premium standard. Its exceptional strength-to-weight ratio recently allowed for a 40% weight reduction in F-16 landing gear braces by substituting high-strength steel with silicon carbide-reinforced titanium MMCs. In the high-heat regime, nickel remains the gold standard for turbine components because of that crucial gamma prime stability. However, cobalt matrices are emerging for severe tribological environments due to their superior wear and abrasion resistance. As you can see from the 3D plot, as we increase the weight percentage of reinforcements like molybdenum disilicide or titanium carbide, we see massive gains in micro-hardness, allowing these components to retain structural integrity even in the most severe abrasive environments. Our reinforcement arsenal is divided by performance. Technically mature additives like silicon carbide and aluminium oxide are the standards for aluminium. For extreme wear or armor, we look to the hard phases like boron carbide and tungsten carbide. Looking forward, the next gen belongs to carbon nanotubes and graphene, which offer unmatched tensile load transfer, though they remain highly prone to agglomeration during processing. One of the most exciting emerging paradigms is the use of high-entropy alloys as matrices. HEAs solve the traditional trade-off of limited yield strength through severe lattice distortion. When we incorporate silicon carbide particles into an HEA matrix like iron, cobalt, chromium, manganese, nickel, we trigger a massive microstructural refinement. In fact, studies show the yield strength can jump from a base of 136 megapascals to a staggering 2,522 megapascals in the composite version. As practitioners, our greatest hurdle is the thermodynamic mismatch between molten metals and ceramics. Raw ceramics have high surface energy and low affinity for liquid metals, leading to poor wetting, angles greater than 90 degrees. This leads to particle rejection and porosity. To move from a defective monolith to a synergistic composite, we must lower that contact angle. The solution is interface engineering. By applying metallic coatings like nickel or copper to our reinforcement particles, we dramatically lower the contact angle. For example, a nickel coating can drop the graphite on aluminium contact angle from 140 degrees to just 4 degrees. This facilitates the creation of beneficial intermetallic bridges, while silver coatings can suppress the formation of brittle, detrimental phases like aluminum carbide. Now let's look at the build dynamics in directed energy deposition. High-temperature gradients drive Marangoni convection, circulating liquid toward the pool's bottom and increasing metallurgical bond strength. Our goal here is a delicate balance. We must optimize the aspect ratio to prevent edge collapse while minimizing the dilution rate to retain the reinforcement's mechanical properties. Solidification dynamics, mapped here via the temperature gradient, G, and solidification rate, R, dictate final component isotropy. Notice the reinforcement effect in the EBSD mapping. Adding targeted volume fractions of silicon carbide acts as a nucleating agent, severely refining grain size and creating a more homogeneous, equiaxed microstructure compared to unreinforced alloys. Instead of just adding particles, additive manufacturing allows for in-situ reactions. By driving diffusion couples between the matrix and raw additives, like the titanium boron carbide system, we create finely dispersed thermodynamically stable phases like titanium diboride and titanium carbide during the print. These newly formed phases exhibit superior interfacial bonding compared to ex-situ added particles, radically enhancing fracture toughness. To simplify the selection process, we've developed this guide. If your mission stressor is lightweight structural, think AA 7075 with nickel-coated silicon carbide via laser powder bed fusion. For thermal management in electronics, copper reinforced with silver-coated diamond via liquid infiltration is your optimal route. This table serves as a foundational roadmap for matching stressors to methods. The ROI is already being quantified. We see it in the F-16 landing gear, where titanium MMCs replace steel for a 40% weight saving. We see it in automotive propulsion for Porsche and Toyota, where selective silicon carbide reinforcement in cylinder liners drastically lowers friction. And we see it in the Hubble telescope, where aluminium graphite composites provide the zero outgassing and strict thermal expansion control needed for waveguide masts. Looking ahead, the next era of MMC design is shifting from trial and error to deterministic voxel-level engineering. By integrating machine learning predictive models, we can dynamically adjust laser power to prevent agglomeration and perfectly tune the dilution rate in real time. True mastery of extreme environment design relies on controlling the interface as precisely as the ingredients themselves. If you found this technical overview valuable, please subscribe to stay updated and join our community as we continue to push the boundaries of emerging technologies in additive manufacturing. Thank you for watching.